This is chapter 8. In this chapter, we're going to focus on molecules, particularly covalent molecules with the structure and shape and so on and so forth. But to begin with, I'd like to talk about the bonds, and I'd like to use this few minutes to summarize what we have learned about atoms, ions, cations, especially from chapter 7, to summarize what are these two bonds going to look like. Ionic bond, we understand it is the electrostatic attraction between cations and anions, and we understand that it is the metal loses the valence electrons to become cation. Non-metal gains enough electrons so that it can have an octet. Once we have cations and anions, and there's going to be attraction between them. And for the process here, we understand it is the transfer of electrons between the metal and the non-metal. In other words, the ownership of electrons when we talk about a chemical bond is that electrons owned by the anions. Metal loses electrons, that's it. Metal does not claim any ownership, I'd like to say, about that electron it loses. That electrons owned by the chlorine. As we can see, after lose the electron, sodium becomes much smaller as a cation, while chlorine becomes the chloride with a larger size. And there's no bond restriction. The reason for that is once you have a cation and anion in space, they are going to attract as many oppositively charged ions as possible. In order to maximize their attraction, they form a three-dimensional network, or we call ionic ladders. In this way, in an example of sodium chloride, we see that for each chloride anion, it attracts 6 sodium cations. Same thing for cations as well. For each sodium cation, it will attract 6 chloride anions. So for example, if you look at this chloride, for example, this chloride has 1, 2, 3, 4, 4 sodium cations. And I'd like to remind you there's a one behind and a one in front. So there's a total 6 sodium cations for each chloride. In order to make a charge balance, it has to be 6 chloride for each sodium cation. In this way, they can maximize their attraction so that the ladders become very, very stable. So stable, they have a very high boiling point and even much, much higher. They have a much higher melting point and even much, much higher boiling point. And we understand that we have to use the empirical formula, but here we call the formula unit to show the cation anion ratio in the formula. We call NaCl. Does not necessarily mean there's going to be one cation and one anion. We only let people know there's ratio between cation and anion that is 1:1 in the case of sodium chloride. And of course, there's no existence of molecules in any ionic compound because they are ions. There are no such molecules exist. As for covalent compound, situation is going to be quite different. When two atoms approach each other, so for example, this is a hydrogen nucleus, this is another hydrogen nucleus. As these two hydrogen approach to each other, once they get close enough, the electron of these two hydrogen atoms start to pair up each other, because once they form the pair, they have 2 units of negative charges, so they can provide enough attraction to these 2 nuclei and let them stay together close enough. As you can see, from a pair, there's going to be 4 attractions versus 2 repulsions. And of course, the repulsion between 2 electrons is so minimal we can actually ignore because they can stay as far apart from each other as possible as long as within this H2 molecules. When we look at this compound or this molecule here, so we realize for the covalent bonding, it is between the 2 nonmetal elements or 2 nonmetal atoms. They could be the same, of course, in the case of H2, they're the same element. And speaking of electron ownership, they share that pair of electrons. In this chapter, we call it bonding pair of electrons. And such bond is what we call the covalent bond. Just like this bonding illustrated in the hydrogen molecule, we realize there's no covalent bond beyond the bonding atoms. So that means, of course, we are not going to see there's some sort of attractions to another atom of hydrogen or any other atoms. This does not exist. So that is what I meant by no covalent bonding beyond the bonding atom. That is only exists between the 2 bonding atoms for this pair of atom. This pair of bonding electrons. One conclusion we can draw from what we have just discussed is that bonding electrons are pretty much localized within the molecule. In the case of H2, there's just one bond, covalent bond between those 2 hydrogen atoms caused by this pair of electrons we call the bonding pair. It does not go beyond molecules or does not go beyond atoms even. So that is why covalent bonding is localized. That is a very important property or feature about the covalent bonding. Because for organic chemistry later on, the localized covalent bond becomes quite an interesting topic. Alright, since the bond cannot go beyond the bonding atoms, those bonding atoms form the smallest unit in order to repeat themselves. That is why we got the molecules. As we've shown right here, it doesn't have to be 2 hydrogen atoms, it could be the 2 nonmetal atoms like a chlorine and a bromine, and they form a bond as we see right here. They form a bond, you see right over here, and that bond does not go beyond this molecule. It only exists within that molecule. And of course, they can form many, many molecules and flying around and do whatever they want to. Speak of sharing electrons, I'd like to remind you, according to atomic theory that we have discussed in chapter 6 and chapter 7, we realize that this electron we call a pair, they may not stay as close as we thought. For example, this is the model of the hydrogen molecule. And we have 2 nuclei of hydrogen stay close together, like 2 yolks. And as long as within the eggshell, this is where we find the electrons. These 2 electrons we call it as a pair. Let me put it this way. The pair of electrons is what we think those electrons should do. Whether these electrons do the bonding pair or not is totally unknown. Bonding pair is just what we think those electrons will behave. That's it. So far, we have discussed the 2 major bonding that we see in a compound. Okay, so one is ionic bond, one is covalent bond. There's going to be the third bond, of course, that is way beyond the scope of general chemistry. That bond is metallic bond. But there's going to be a challenge because we always want to see whether you can unify these two bonds under one model, because that would be a lot easier for us to discuss. Once we propose something, and they will take care of both of the bonds. Many people have tried this way, and it has done by certain chemists. His name is Linus Pauling, and this is basically what he thought about how he's going to unify those two very much different chemical bonding under one concept. Let's look at covalent bond. We understand covalent bond is a valence electron pair shared between atoms. I'd like to remind you, those valence electron pair is what we thought those electrons are going to act. Whether this is these two electrons, we don't know. But we just thought, okay, electrons can find another electron forming pair so that it can hold those atoms all together. And for covalent bond, valence electron pair shared between atoms. And I can think of two cases. The first scenario, those valence electrons pair shared equally. In the case of hydrogen, right? Those nuclei has the same attraction toward that bonding pair. So we can imagine that a pair of electrons are going to stay right in the middle, 50-50. They do not go over one atom, because the moment they go over too close to the atom 2, atom 1 will take those electrons back right in the middle. This is the scenario we can think about valence electrons being shared equally. Or another scenario, say one of the hydrogen atoms has been replaced by the fluorine. From last chapter, we understand fluorine or any other element in that particular group 7 is highly reactive because they want just one electron away. They just want one more electron so that they can have an octet. Between hydrogen and fluorine, fluorine shows much attraction to that bonding pair. In other words, that pair of electrons is going to spend more than 50% of the time on fluorine. That means when bonding, if we take the average, fluorine not only get its electron back, and it also gets some of the electrons from hydrogen towards itself. That is the reason why, as you can see, that one of the atoms, in our case fluorine, has some kind of a negative charge. Hydrogen will have some kind of a positive charge. Why is something that we're going to discuss later on in our second half of the chapter of 8. That is what we call second scenario, where we see the valence electron pairs no longer equally shared, because it's no longer 50-50. That could be 30 versus 70, so on and so forth. You may wonder if there is a 100%, 0% to 100%. Now let's take a look at lithium fluoride. We can think of the bond formation of lithium fluoride in 2 steps. First step, lithium just like hydrogen. Remember, lithium hydrogen is in the same group, right? So at the very beginning, lithium could just form a bonding pair with fluorine. Why? Because if we look at the electron configuration for lithium fluorine, we realize, okay, lithium has a 1 electron unpaired. According to Hund's rule, fluorine has a 1 unpaired electron in its 2p subshell. Those 2 unpaired electrons pair up. Perfect, right? Those electrons are paired, and we got a pair of electrons stay between the lithium and fluorine, and voila, we have a covalent bond. But once this bond is formed, lithium starts to think about just what I'm doing here. Because by forming a bond, lithium could have namely 2 electrons to itself. One from itself, the other one from fluorine. But just how many electrons does lithium need to have an octet? 2 ways for lithium to reach the octet, right? Because lithium could gain 7 more electrons so they can have an octet with the same electron configuration as neon. Or lithium could just give up that valence electron so that it can have a helium core. While losing that electron to the fluorine, fluorine will have a neon core. That is a win-win situation for both of these atoms. That is the reason why the moment that they start to form so-called bonding pair, second step takes place. Because lithium just give up the ownership of that bonding pair. That bonding pair goes completely to fluoride, 100% for ownership. In this way, covalent bond becomes to ionic bond because one atom owns the bonding pair towards itself 100% of the time. Since it's 100% of time, atoms become ions. The bond becomes ionic bond instead of covalent. What I'm trying to say here is when we look at the formula of these 3 compound substances, we realize that we can unify these 2 bonds by checking out just how easy for an atom to attract that bonding pair towards itself. Fluorine, much easier. That is why it becomes an anion by bonding with lithium. Or it can have more than 50% of time for this bonding pair towards itself. It cannot be 100% because hydrogen still fight for the ownership of that pair of electrons. So all of this has come to one statement. Now the only ionic bond is an extreme of a covalent bond, and a type of bond actually depends on how strong the atom attracts the bonding pair towards itself. If fluorine is too strong compared to its counterpart, it's going to be ionic bond. If fluorine is not so strong, too strong compared to the counterpart, like a hydrogen, we have a covalent bond. If these 2 are equal, so that's going to be equally shared covalent bond. All right. So once we have this in mind, a new concept called electronegativity is proposed by Linus Pauling. So he states that electronegativity, we should call it EN, is the ability of an element to attract the bonding electron pair to itself within a covalent bond. That means when we have 2 atoms start forming a bond, it's always going to be a covalent bond first. Depending on how strong that atom to attract that bonding pair from a covalent bond, it could be an ionic bond as a result. Just like the statement we said, ionic bond is an extreme of a covalent bond. Dr. Pauling also did the calculation on this, and those values has been shown right here. Apparently, we realized that the noble gas element in group 8A shouldn't have any electron activity because they are not interested in gaining any electrons, just like they did not show much of an interest to lose electron. Electron activity to them is pretty much 0 is not good, even a good number to describe. So that's why we do not consider the value of their electron activity. But when we look at starting with the second group right here, we start to see there's a periodical train. As we cross period from left to the right, electron activity increases. From lithium 1.0 all the way up to the fluorine, which is 4.0. That thing also repeats itself in the third period. From 0.9 all the way up to 3.0. There's no exception there. Down the group, the general pattern is that the electron activity decreases as we're going down the group. But for group 3A and 4A, we start to see something quite interesting. And electron activity decreases, and then we start to see gallium and indium electron activity increases. That's particularly more obvious in group 3A than it is in group 4A. The reason? Something very similar as we explained when we try to talk about the periodical train of atomic size in the previous chapter. Alright, so I just want you guys to understand that there's another periodical train that is not in chapter 7 but in chapter 8 on electron activity. So we have 3 periodical trains that we have talked about. Okay, so we have atomic size, we have periodical train, all of which have something to do with nuclear charge, which is also have the periodical trains itself. When we look at those values, another impression we have here is, in general, metal has lower electron activity than those of nonmetals. That's true. That's true for the main group of elements right here. And also we called 4 electron hogs for those elements: fluorine, oxygen, nitrogen, and chlorine. Fluorine has the most electron activity, and hydrogen is the second. Nitrogen and chlorine, they are the same, and put it together as the third prize, number 3. And one more thing I'd like you guys to keep in mind is that hydrogen has the value of 2.1, and we consider hydrogen as the least electronegative nonmetal element. Of course, you may argue, hey, we got a boron 2.0 here. Why should we consider hydrogen? Because if we consider hydrogen as the least electronegative nonmetal, that means hydrogen is the element has the least attraction to the bonding pair when forming covalent bond with the other nonmetal element. However, hydrogen, since it's a nonmetal, and it will form ionic bond with a metal to have that bonding pair of electrons completely towards itself. So few things other than periodical trend of electron activity, I want you guys to understand first, how do we know in general about the difference of electron activity between metal and non-metal? And what are the 4 electron hogs? Which one is the most electronegative? Which one's second? And the last, hydrogen. We label hydrogen as the least electronegative non-metal in Chem 1 course, so that we understand that hydrogen will behave quite differently when it bonds with non-metal and when it bonds with the metal. Okay, we can definitely explain the behavior of atoms in forming compound or the molecules using our knowledge of quantum mechanics, quantum numbers, remember, electron configuration, so on and so forth. But that is going to become quite complicated. Okay, so that is why, as you can see, we have chapter 9. So that is going to be a modern treatment of covalent compound or molecular compound using the electron configuration or the new treatment of the quantum to explain the whole thing. But here in chapter 8, we just use some, I prefer like a common knowledge or some sort to explain how those molecules can be formed or compound can be formed. This is done by Lewis, Gilbert and Lewis. In 1916, he published an article. This article make the chemistry very much different from then on, because he just used a very simple idea to explain the molecules or compounds so complicated and so beautifully, so splendid, and sometimes people even without a math background can understand the whole thing. He introduced the dot to represent those valence electrons. So he said, I'm going to use a dot, one dot, to represent one valence electron of that atom, particularly those atoms in main group elements. So as you can see here, lithium, we understand it's group 1A, one valence electron, so that's one dot. For atoms in group 2A, and there's 2 dots. Why we have 2 dots, not paired, but in a different side of the chemical symbol? Because he said 1 dot on each of the 4 sides of the element symbol. That means those dots do not pair themselves at the very beginning, kind of like Hongzhu. Remember, one electron starts to occupy then subshell with multiple orbitals. Electron intend to occupy different orbital first, right? So that's part of Hong's rule. And here in Lewis model, dot model, so those valence electrons, they pretty much going to behave the same way. Only this time, it's going to be 4 unpaired dots before they pair. Because carbon has 4 sides. As a matter of fact, each element symbol has 4 sides, right? And each side will have 1 dot. And from nitrogen, 5A, 5 valence electrons, first 4 will go each side, and the 5th one got nowhere else but pairing. So from this discussion, now we understand if we have an atom in group 1A to 4A, those dots are not paired. From 5A to 8A, those dots start to get paired. And finally, we realize that if we have atoms in the same group, since they have the same number of valence electrons, they will have the same number of dots. Here, I'd like to point out, since they have the same number of dots according to this model, Lewis dot model, they will have same dot, we call dot configuration. For example, if I got a silicon has a 4 valence electrons, those 4 dots will not pair themselves, just like they are in the carbon. Neon got got 4 pair of electrons. And of course, we understand it's going to be the octet, right? So 8 electrons in 4 pairs. The octet in Lewis electron dot model is 4 pairs of electrons. Hydrogen duet. We understand hydrogen requires only 2 electrons to have this principal shell completely filled. Hydrogen is going to be happy about this situation. Once we have a pair of electrons that's owned by this particular atom, we call it the lone pair of electrons. For example, nitrogen. So this neon has 4 pairs of electrons. Each pair is going to be called as a lone pair. Here, I'd like to point out a little bit about the difference between Lewis dot and electron configuration. Because we remember, if we have elements in group 2A, 3, and 4A, remember we have NS2, NP something, right? And we should have a pair of electrons in the same atomic orbital. But here, we just don't see any. Why? That is because this model was proposed almost 20 years before the quantum mechanics was used to explain the atoms. And of course, in chapter 19, we'll come up a mathematic way to let people to understand, okay, it may be just turn out there could be 4 unpaired electrons of carbon in order to form covalent compounds. But we just don't have time to explain all that because that one week that we are off after the spring break. This loose thoughts about those elements can explain the ionic compound perfectly. That is why, so they start to persuade people to accept this model. It's a simple but very, very effective. Now let's look at the compound, the lithium fluoride, the one we used as the example before to unify the ionic and covalent bond all together. We understand lithium has a 1 dot, 1 valence electron. Fluorine group 7A has a 7 dots because it has a 7 valence electrons. And the lithium is the metal, fluorine is the nonmetal. We understand that it's going to be an ionic compound. Okay, so this is the electron configuration as shown. And once they form an ionic compound, we realize the metal is going to lose electrons. Just how many electrons the metal atom is going to lose. From previous chapter, we said main group metal will lose their valence electrons, right? Here, according to Lewis dot, those dots represent valence electrons. So metal is going to lose all the dots. There will be no dot whatsoever left around the symbol. In chapter 7, we understand by losing valence electrons, metal atom will have intermediate proceeding noble gas as its core, which is the octet to satisfy. So the total number of charge plus charge is equal to the total number of dots that the metal loses. So in our case, lithium loses only 1 valence electron because it has only 1 valence electron. So we see that the lithium is going to have a helium core once it becomes +1 charge. And fluorine got that electron transferred from lithium, becomes fluoride, which has the same electron configuration as neon. And speaking of anions formed by non-metal, anion will gain enough dot to fill out the valence shell, which is 4 pairs, 8 dots around the symbol. Regardless of what charge that is, it has to be 8 dots first. It means 4 pair electrons, each pair, so 1 pair on each side of this chemical symbol. The number of negative charge will be the number of dots that non-metal atom gain. Okay, just how we're going to figure out the formula by this way. Charge balance. Number of electrons lost by metal must equal to the number of charge electron gained by the non-metal. So if we have a lithium fluoride, we have 1 positive charge, 1 negative charge, put them all together, charge cancel, so we got a neutral compound. So this loose dot explains ionic compound splendidly, beautifully, very efficient. So people try to start to use that model to explain a covalent compound a little bit further. For covalent compound, our challenge here is there's no obvious electron transfer. Because we are talking about the covalent bond, we're talking about the bond between the 2 non-metal atoms. There's no obvious charge transfer because either atom will fight for the ownership of this bonding pair of electrons. So here I lay out some of the common non-metal atoms representing those in the different groups. Just how we understand that the covalent bond is going to be formed. For example, if you look at carbon. The basic strategy is, since there's an ampere dot, the ampere dot must be paired. Remember, 4 pairs is the ultimate goal for each atom that we list in this slide, except for hydrogen though. 4 pairs means the octet. If I got a carbon with a 4 unpaired dot, those 4 unpaired dots are going to find a way to pair themselves. So basically our strategy is to pair those unpaired dots with other atom in order to have an octet, duet for the hydrogen. In this way, so we can look at just the situation about each element in this particular group as a representative, because the rest of the non-metal element will behave pretty much the same. And by checking out the valence electrons, whether they have lone pairs, and just how many unpaired electrons, valence electrons are going to be, so we should be able to predict just how many bonds these elements will form. Remember, hydrogen is going to be duet. The rest of the elements, as I said, the p block elements, right? All the non-metal elements except for hydrogen can be located in the p block in our periodical chart, our periodic table. So I would call them p block, the non-metal element. They're gonna have an octet. All right, so let's start with the hydrogen. Hydrogen, we understand that it's going to be 1 valence electron. Any lone pair all by itself? Apparently not. So there's only 1 unpaired valence electron. How many bonds is going to be? 1. Because by forming 1 bond, by sharing this electron with another electron from the other atom, hydrogen is satisfied with duet. Although it is not 100% of ownership, maybe just a 50-50, 50% of the time, it is a duet. A good enough compromise in order for hydrogen to have a duet. Same argument for carbon. 4 valence electrons. Those valence electrons, those dots are not a pair, so that's why we do not see any lone pair. Those 4 unpaired valence electrons are going to be pair themselves. How many bonds is required? 4 bonds. And from this discussion, you guys can see there's going to be 3 bonds for nitrogen because they got 3 unpaired dots, 2 unpaired dots for oxygen, and only 1 unpaired dot for fluorine. So fluorine needs only 1 bond, just like hydrogen. And that is not a surprise to see that the Mother Nature chooses carbon, nitrogen, oxygen to form all kinds of substances that we use in biology. Even us are made of carbon, or made from carbon, nitrogen, oxygen, and hydrogen. But I just like to point out here because later on we'll see why hydrogen and fluorine are so special when we write the formula using loose dot, because both can only form 1 bond and 1 bond only. So by checking on the number of unpaired electrons, we will know just how many covalent bond is going to be, because unpaired electrons is going to be paired. In mathematics, number of covalent bond will be 8 minus the group number, or 2 minus the group number for hydrogen. Now, with that knowledge, so those dots are going to find a way to pair themselves when the atom meets with another. The simplest molecule we can think about is 2 atoms, right? So if we have 2 atoms start to approach each other, so say we got 2 halogen atoms. Those X could be the same element or could it be different? Because nevertheless, those atoms in that group 7A have 7 dots, leaving only 1 dot unpaired, as you can see right here and right here. As they approach to each other, those 2 dots obviously are going to form a pair that hold these 2 atoms together. That is why we have diatomic molecule. And for each atom X, they're going to have an octet at least 50% of the time. Okay. In chemistry, we use a dash to represent. The bonding pair. The dash is what we call bond. Chemical bond. Hydrogen will do the same because hydrogen requires only duet. That means if we have 2 hydrogen atoms approach to each other, and those unpaired dots start to pair themselves, right? We have here, and we got another bond. And since there's only 1 pair of electrons, remember when we say pair, 1 pair of electrons, it means 2. And that a single dash represents 2 bonding electrons. That the 1 bonding electrons hold that the 2 atoms together is what we call a single bond. Do we have any other bonds? Yes, we do. We can have a double bond and a triple bond. Double bond means 2 bonding pairs of electrons between the bonding atoms. Triple bond, of course, is 3 bonding pairs. 3 bonding pairs. How many electrons between the 2 bonding atoms? 6. Remember, each pair has 2 electrons. Oxygen would be a very good example to explain how a double bond is formed. As we see the 2 oxygen atoms start to approach to each other, and these 2 unpaired dots start to pair themselves here. And apparently that's not going to be enough, because as we try to count the electrons around that single atom, including that bonding pair, that is going to be 1, 2, 3, 4, 5, 6, 7. 7 dots, 3.5 pair of dots around each atom. That is not good because remember, octet is automatic goal for atoms like oxygen. So what are you going to do? Oxygen, those two oxygen atoms, just realize they still have a 1 unpaired dot that needs to be paired, right? So they're going to put that unpaired dot into the bonding region. So that is why we have those arrows to show, okay, so that electron goes into the bonding region. And since we got 2 more electrons going in the bonding region, so we have 4 electrons forming a chemical bond. 4 bonding electrons, meaning 2 bonding pairs. 2 bonding pairs, we have 2 dash to represent such double bond. Triple bond occurred also in the molecule of nitrogen. Remember, nitrogen has 5 dots, 3 unpaired, 1 paired, okay, 2 of which are paired. And again, as these 2 nitrogen atoms are paired, so approach to themselves, we realize there's going to be a single bond to begin with. For each nitrogen, 1, 2, 3, 4, 5, 6. It's not going to be good because nitrogen is going to be octet eventually. Just like oxygen, they give up a 1 unpaired dot to the bonding region to form a double bond. Is that going to be enough? Let's count. 1, 2, 3, 4, 5, 6, 7. Still 1 dot short to have an octet for each nitrogen. Again, they realize they have the 3rd unpaired dot, which they can put in the bonding region. In this way, we have 6 electrons in the bonding. And only in this way, we realize each nitrogen has an octet. 1, 2, 3, 4, 5, 6, 7, 8. And we have a triple bond right here. 3 dashes to represent total 6 bonding electrons. So that is probably the way that your teacher told you to write up a loose structures for many covalent bonds. You just put those atoms together with their own loose structures, loose dot, and start to pair those unpaired dots. This approach works quite good, but not perfect because in carbon monoxide, there's going to be a problem. We understand carbon has 1, 2, 3, 4, 4 unpaired dots, oxygen has only 2. As they approach each other, that's a single bond, not going to be enough because neither atom reaches an octet. So 1 unpaired dot from each atom goes into the bonding region again, and this is what we have. And there's going to be a problem. Carbon has only 6 dots, while oxygen has 8. With this particular structure, people will understand this carbon monoxide, CO carbon monoxide, is going to be extremely unstable. As it turned out, it's not. It's a quite stable gas. Reactive, yes, but itself is quite stable. We can store it, right? We can put it in the tank for a very, very long time. What does that mean? It means this loose structure is wrong. Because this structure cannot explain the chemical property of CO in reality. That is the reason why I would like to introduce a procedure writing Lewis structures for covalent compound. Polyatomic anions also can be included here. This method I like to call is playing God method, because what we're going to do here is we take away those valence electrons from all bonding atoms. We arrange those atoms with our rule, and then we give those valence electrons back with a much better arrangement, so that we do not have to see the situation like a carbon monoxide if we let those dots pair themselves. All right. Since we're going to take away those valence electrons, meaning we have to know just how many valence electrons we're going to play with. So this is how we're going to calculate. We're going to add up the valence electrons from each atom so that we know just how many valence electrons in total. If we have ions, like a polyatomic cations or anions, we're going to add 1 electron for each negative charge. Negative charge means 1 more electron, right? So we just add 1 electron. And we're going to subtract 1 electron for each positive charge, because positive charge means electron deficient. Once we know just how many valence electrons that we have for such a formula, we're going to set up atoms, particularly central atom. We pick the central atom, the one with the least electron activity. That is the reason why we have to introduce electron activity to begin with, and we have to understand which one has a higher electron activity than the other, or vice versa. Because the one with the least electron activity must sit in the center, except for hydrogen. Later on we'll explain why, but I believe I already point out why hydrogen cannot be the center atom, because hydrogen requires only 1 bond. The subscripts for the atom that we picked as a central atom, meaning that we're going to have multiple central atoms. Then we arrange surrounding atoms, or we call it terminal atoms, and with a certain symmetry. One thing I like to point out, if we want to do acid, hydrogen must attach to oxygen, because that is the matter of fact. We cannot just put hydrogen on the central atom unless we are told specifically. So once we arrange those atoms, we give back those valence electrons. But we give the electrons back through certain steps. First step, we just give 1 bonding pair, a single bond between each pair of atoms. Why? Because we just want to let people understand those atoms are chemically bonded. By what kind of bond? Covalent bond. Whether that bond is sufficient, that's something that we are going to deal later. But we just give each pair of atoms or pair of bonding atoms with a single bond to let people know they are chemically bonded in this molecule. Most of the time, we're going to have extra electrons. So once we have the extra electrons, we make octet for surrounding atoms first. Because I like to say 95 to 98% of the time, there will be sufficient number of electrons to have octet of surrounding atoms. To make the surrounding atoms octet. They're always going to be. Now, I'll take it back. I do not have to say always, but it's almost always true to have enough electrons or valence electrons to have surrounding atoms octet. Then we only have one atom left, central atom. If we still have more electrons, then we need to distribute or assign. We assign to the central atom. It is quite possible that we do not have enough electron to make an octet to central atom. Then we just have to move one lone pair electrons from terminal atom to the bonding position between atoms. In this way, that the bonding pair, the lone pair of electrons from terminal atom or surrounding atom that used to be owned 100% by terminal atom or surrounding atom, now it's being shared between itself and the central atom. In this way, central atom will definitely find a way to attain the octet. Because we just move one lone pair of electrons into the bonding position, you're going to have double bond or triple bond between the terminal atom and the central atom. So that is the reason why we see double bond or triple bond in some of the molecules, because central atom must be an octet. For ions, polyatomic cation or anion, there's one more step for us to go to. We just simply bracket the structure with the charge on the upper right corner, because without a charge, to let people to know, people will realize that we have the wrong calculation on the number of valence electrons. So it is our responsibility to let people to understand this is why or how we calculate valence electrons based on the charges. We have to let people understand those things do have charges. So that's why we put a bracket around and let people to know what the charge that is. Now let's look at an example here. Let's redo the carbon monoxide using our approach. Remember that those unpaired dot pair themselves failed for carbon monoxide. Now let's see just how good our approach is. First step, we calculate total number of valence electrons. And if you look at the carbon and oxygen in our periodic table, carbon is in group 4A. Remember, group number indicates the number of valence electrons. Number of valence electrons can be represented by the dots. So there are going to be 4 dots for carbon, 6 dots for oxygen, because oxygen is in group 6A. I just hope that you have a periodic table by your side so that you can check out whether I said it correctly. CO means 1 carbon atom, 1 oxygen atom. So 1 times 4 plus 1 times 6. We know there's going to be 10 valence electrons to distribute. It's diatomic molecule, so it doesn't matter which one's on the first, but by convention. The least electronegative element comes first when we arrange atoms or write a formula. I just want to have you guys realize when we in chapter 2 writing a formula, we said we start off the elements on the most left hand side and we end the formula with the element on the most right hand side. Now remember from the period, in the period from left to the right, electron activity increases. So at the end of the formula is the element with the greatest electron activity. This is how we write the formula. Well, this is an episode. Alright, so we set up a carbon and oxygen. Carbon first, and we distribute the electrons. Remember, single bond for all pair of a bonding atom, we only have one pair, so we gave 2 electrons. So that's 2 of the 10 being used. We still have 8 more. Here I'm going to consider oxygen as the terminal atom because carbon is less electronegative. Oxygen is the one with the more electronegative. So I'm going to give enough electron to make an oxygen octet. How many more? 6 more. In 3 groups. 1, 2, 3, 4, 5, 6. So in 3 pairs. Alright, so that's a total 8 electrons that we used. And remember we have 10 electrons. So we're going to give the 2 electrons to carbon. Now we used up 10 electrons. But the carbon still have 4 electrons, right? 2 bonding pair electrons and a lone pair electron to itself. So what are we going to do? Remember, in order to make an octet for central atom, terminal atom has to give up the lone pair of electrons, enough lone pair electrons to the central atom in order to make it an octet. Carbon needs 4 more electrons, requiring 2 lone pairs of electrons from oxygen. So that is the reason why we start to see these 2 lone pair of electrons of oxygen going to the bonding position. We got yourself a triple bond between carbon and oxygen in such compound. In this way, either atom will have an octet with 1 lone pair in each atom. And they had 6 bonding electrons between them. And those 3 dashes represent 3 bonding pairs of electrons. And also, I want you guys to notice that each atom will have 1 lone pair to themselves. So that's why we have a total 2 lone pairs of electrons. And I'd like to try out another carbon oxide called carbon dioxide, because you may realize carbon monoxide is a toxic gas. Very small dose could cause the death of a person. However, carbon dioxide is not. Carbon dioxide is much, much less toxic. And what's the difference? I'm just curious. So that is part of the reason why I'd like to try the loose dot structure for carbon dioxide. As we count the total number of valence electrons, again, carbon brings in 4 dots. Each oxygen will bring in 6 dots, making a total of 16 electrons. And this time, carbon is going to be in the center because carbon is the less electronegative, because carbon is on the left-hand side of oxygen. Remember, across the period from left to right, electronegativity increases. That means oxygen is more electronegative than carbon. Okay, so carbon in the center is surrounded by 2 oxygens symmetrically. As we distribute the electrons, now we have 2 pairs of bonding atoms. So that's why we give up total 4 electrons to have 2 single bonds between carbon and oxygen. Each pair. And for the rest of the electrons, again, as we established, oxygen atoms are the terminal atoms. So each oxygen will have 6 more electrons as lone pair. And that makes total 12 electrons, plus 4 that are being used for chemical bonding. We used up all the electrons. In this case, we still see carbon has got 4 electrons. Now, good enough. That is the reason why carbon will call off 1 lone pair from each oxygen to join so that the carbon can have an octet with a double bond on either side. And if you remember, for carbon monoxide, there is a one lone pair on carbon. In carbon dioxide, there's no such lone pair on carbon anymore. That makes the huge difference. Because once we have a lone pair of electrons on carbon, that makes the whole difference. That makes the compound extremely toxic. Before we leave, I'd like to discuss a little bit more of these loose dot structures with an anion, polyatomic anion, because I want you guys to realize how we're going to add some extra electrons. As we try to calculate the total number of valence electrons to begin with, carbon 4 dots, nitrogen 5 dots, because nitrogen is group 5A, and 1 times 4 plus 1 times 5, we're not done because we need to add one more electron. Why the one more electron? Because cyanide, Cn minus, has one extra electron because it's one negative charge. Alright, so that is why we make it a total 10 electrons. As we set up atoms, just like CO, we put carbon in the front, nitrogen second, because nitrogen is on the right, more electron negative than carbon. As we distribute the electrons, and we got single bond between carbon and nitrogen, 6 more electrons on nitrogen to make a nitrogen octet. That leaves only 2 electrons going to the carbon. And nitrogen is an octet, carbon is not. Just like what we did to carbon monoxide, nitrogen is going to give up 2 lone pair of electrons home to the bonding position. In this way, carbon, nitrogen, each atom will have 1 lone pair of electrons to themselves with the 6 electrons in between. We're talking about a triple bond between carbon and nitrogen. And as I said, this is an anion. In order to show the difference on how we calculate the valence electrons, we need to put them within the bracket and let you understand they have a 1 negative charge. Here, I'd like to put carbon monoxide along, so you will see just how similar their structures are to each other. Triple bond, 1 lone pair on carbon, 1 lone pair of carbon. That is the reason why either species can kill a person with very small dose, because it is this lone pair of electrons on carbon that deactivate iron in our hemoglobin in transporting oxygen. It deactivate the iron 3 plus inside of the blood that is in hemoglobin. And since we see the similarity in the structure, so we call these 2 compounds, the 2 species, isoelectronic. Because we see 2 or more molecular entities that can have the same number of valence electrons and the same structure. For example, diatomic. Alright, before we talk about the VSEPR, few things I like to point out. First, when we write up a formula from now on, we do not always put the least electronegative element in the first place. It is up to us to decide which one should be the central atom by checking out the electron activity or by checking out the location of the element in the periodical chart. So it is the least electronegative atom that should be considered as a central atom, except for hydrogen. Subscripts of the central atom indicates just how many central atoms we have. So for example, C2H2, both carbons should be considered as a central atom, while hydrogen must be the terminal atom. And for oxo acids, hydrogen must attach to the oxygen. So when we look at this case, between oxygen and chlorine, we understand that chlorine is less electronegative, so chlorine should be considered as a central atom because it's less electronegative. But the third atom has to go to the oxygen instead of chlorine because it's an acid. That's, in fact, make oxygen the central atom, not the chlorine. Because hydrogen has to bond with oxygen by the definition of oxo acids. Fluorine and hydrogen can never be considered a central atom because they both need a single bond and a single bond only. Being the central atom, the atom must have a capacity to have at least 2 bonds. That is the reason why hydrogen fluorine can never be considered as a central atom. Now let's look at some example or one example about multi-central atoms. This compound is called hydroxyamine in organic chemistry. And the reason why we split the hydrogen in 2 different positions is that we understand these two hydrogen connects with nitrogen, and this hydrogen is connected with the oxygen. And we got 2 central atoms. And from the number of dots that from each element, so we understand that there's going to be total 14 valence electrons. And we put the nitrogen, oxygen in the center, surrounded by the number of hydrogens, indicated by the formula. Remember, formula says 2 hydrogen bond with nitrogen and 1 hydrogen bond with the oxygen. As we distribute electrons, remember, single bond for all pair of bonding atoms. So we get it, all those atoms chemically bonded with a single bond first. 1, 2, 3, 4, 5, 6, 7, 8 electrons have been used so far. Remember, we have total 14 electrons. Between nitrogen and oxygen, I'd like to say oxygen is kind of a terminal atom. Oxygen becomes an octet first. So how many more electrons we put on oxygen? 4 more. So we have total 8 plus 4, so that's 12 electrons. We still have 2 more electrons that has to go to nitrogen. So from this loose structure of this molecule, we realize every atom are stable because nitrogen, oxygen attain an octet, hydrogen reaches the duet. Now let's talk about the second half of this lecture, VSEPR model. VSEPR is short for valence shell electron pair repulsion. Why I put the repulsion on the score? Because repulsion is the key. A lot of things can make sense as long as we think about repulsion among those electrons. In order for us to carry out this VSEPR model, first we need to draw a valid loose dot structure. When I say valid, that means the octet or duet for all the elements in most of cases. In our second half, and we'll talk about some exceptions we might see. So once we finish the loose structure, we focus on the central atom. We do not have to worry about terminal atoms, so we're going to take them away. We ignore them. We just start to count electron groups around the central atom and the central atom only. We count each lone pair as a one electron group. Remember, lone pair electrons will occupy entire one side of the chemical symbol. That's what it counts. If we have electrons occupy the entire one side of a chemical symbol in Lewis dot structure, we're going to count them as one electron group, regardless how many electrons there will be. That is exactly the principle we're going to treat the bonding electrons. For bonding pairs, each bond will count as one electron group, regardless whether it is a single, double, or triple bond. Why? Like I said, I don't care just how many electrons there are on the side, on the one side of a chemical symbol, as long as it is in one side, we count as one electron group. It could be 2 electrons, it could be as many as 6 electrons on one side, we don't care. What happens if there's only 1 electron that occupied one side of this chemical symbol? We count as electron group as well. And of course, in this situation, we would like to call it radical in chemistry. All right, so you just understand what a radical is. As I said, the keywords for this VSEPR is R, repulsion. Since we talk about electron groups, all kind of restrained on the central atom, and they have the same type of charge for electron groups, right? And because of repulsion, they're going to stay as far apart from each other as possible. And once they spread out, in order to reduce or minimize the repulsion, remember, they try to avoid any angle between them which might be less than 90 degrees. Because 90 degrees, that put those two electron groups too close to each other. Most of the time, as it turned out in Gen Chem 1 class, 90 degree is the limit. And the angles between the electron groups can no longer less than 90 degrees. VSEPR theory is used to determine or to let us know what the molecular shape that is. There are a few other names about the molecular shape you can call arrangement of the molecules or arrangement of atoms or molecular geometry, geometry of molecules. You can call pretty much whatever you want, but they all come with the same definition: relative position of the atoms in a molecule or in an ion. For example, if we have a carbon dioxide, it's going to be pretty much like this. We got a carbon in the center with a 2 oxygen on the side. So here is something that explains why we have a sphere, the big one in the center, smaller one on the side, and here E stands for lone pair of electrons. So we now understand that the geometry of this particular molecule, like carbon dioxide, is linear. And also we have a bond angle, because bond angle becomes quite important for us to determine just how many electron groups that we can have on a central atom, or to reduce just how many electron groups on a central atom in a molecule. Bond angle is the angle formed by the nuclei with the two surrounding atoms with the central atom. So as we can see here, so it's a linear 180 degrees. So if we have molecules like carbon dioxide or hydrogen cyanide, and BeCl2 is something you're probably going to see if you watch the video from DeWitt, Tyler DeWitt. Okay. So he used BeCl2 as an example to explain the molecular shape, okay, of that compound. So if we have a linear as molecular shape for such molecule, the bond angle is definitely 180 degrees. It cannot be anything else. That, as we count, there are 2 electron groups on the central atom. Sometimes, in order for us to simplify the situation, I just put the circles on each electron group on central atom and say, okay, so just count those circles. I said 2, so 2 electron groups. For 2 electron groups, remember, those electron groups, by having the same type of charge, they're going to stay as far apart from each other as possible. What is the better way for them to have if they point out to the totally opposite direction with 180 degrees in between? So VSEPR theory does not require a lot of calculations. That repulsion actually tells us, as long as we practice our best with our common sense, the shape of molecules can be easily predicted. As I said, in order to minimize the repulsion among those electron groups, so the electron groups will stay as far away from each other as possible, and we could have 5 fundamental electron group arrangement. As we already talked about linear, so it's 180 degrees, and for 3 electron groups, just imagine if we add 1 electron group from the back side of this picture. Remember, they all have negative charges. So this 3rd electron group will repel these 2 electron groups upwards, right? More towards ourselves. So we have trigonoplanar instead of linear, or T-shape. The angle between those electron groups is going to be 120 degrees. All right, so now let's think about where we're going to put our 4th electron group. And you may realize it's either from the top down or bottom up. From top down, they are equivalent, so it doesn't matter. Because if you flip the picture, what used to be top now goes to the bottom. So from top down, there's a 4th electron group on top will push these 3, as you may see it, downwards. That makes a new geometry we call the tetrahedral for 4 electron group. The bond angle, or the angle between the electron groups, is going to be 109.5 degrees. And if we want to add the 5th electron group, the only place, the best way to do it is from the bottom. And by adding another one, the repulsion will have these 3 electron groups going back to horizontal. Now we have a new geometry we call the trigonal bipyramidal. It is the only geometry for 5 electron groups. The angle here could be 180, 120, and 90 degrees. If we got 6 electron groups, that would be octahedral. And the angle is going to be 90 degrees among them. So far, it's quite clear, but we have a problem with a lone pair of electrons. because lone pair electrons cannot be detected. In other words, we cannot see lone pair of electrons. Why we cannot see the lone pair electrons? Because we do not know which two electrons are the ones we call, quote, lone pair electrons, unquote. That is part of the reason, in my understanding, that lone pair electrons cannot be detected. Okay, if we have a lone pair electrons that cannot be detected on the central atom, we might want up a different molecular shape, even though we start off with the same electron group arrangement. Or we can call it electron group geometry, for that matter. And we're going to see that in our next few slides. All right, so now we realize we can have 3 different electron groups on the central atom. We can have a lone pair, we can have a bonding pair, and we could have just a single electron. But we start off the lone pair first, because when we look at the lone pair, so this is a lone pair electron. Okay, so the picture of lone pair electrons, and this is for the bonding pair of electrons. And what we see here, the difference between the two is, for lone pair electron, there's no atom on the other side to restrain this pair of electrons. Just like this bonding pair, there's another atom to hold this bonding pair right in the middle. Okay, not going in everywhere. Remember, this is a pair of electrons that we assign them to 2 electrons. They have negative charges, so for both, same type of charge, repulsion. So those 2 electrons in the lone pair will stay as far from each other because of repulsion. The best way for them to think about to stay is to stay at the opposite side of the central atom. That is the reason why they're going to occupy the most space around the central atom. As later on we'll see that we describe lone pair of electrons as the Hershey chocolate cone. Okay. From larger side, okay, leaving from the central atom. It's actually the opposite. As you can see here, it's very much like an umbrella instead of a cone shape like this. Because later on we'll see we describe lone pair electrons like a cone with a bigger side out, so pointing out. But we understand that's not going to be the case. For lone pair electrons, it's more like the umbrella of the mushroom. They try to occupy as much space as they can. That is the reason why they're going to squeeze the bond angle about 2 degrees if there are 2 bonds around. In other words, lone pair will have the most repulsion effect. One way for us to understand one simple statement for us to understand about lone pair is the more space is required by the lone pair, because no atom on the other side to restrain this pair of electrons, the greater the repulsion. As for the bonding pairs, now we start to see the difference. We got a single bond, we got a single bond, double bond, and triple bond. Triple bond has 6 electrons that's very much concentrated in the one region, and they definitely gonna occupy more space in order to reduce the repulsion between them. And more space more repulsion. That is the reason why triple bond has the greatest repulsion among all three bonds. As we put them all together, lone pair has the greatest repulsion effect, triple bond second, double bond follows, while single electron radical has the least. All right, we have already talked about two electron groups, and it's linear, and the molecular shape is linear as a result. Now let's talk about the molecules or the species with the 3 electron groups on the central atom. As you can see, there's 3 electron groups. So that's 1, 2, 3. I don't care whether there's going to be an atom on the other end or not. I really don't care. As long as there are 3 electron groups, I can predict the shape as trigonal planar for the 3 electron groups. I like to take it back. I don't think shape is a good word. I like to say the arrangement of these 3 electron groups are pretty much set. It's going to be trigonal planar, period. Whether the molecule will have the same geometry or not is totally dependent on whether there is going to be a lone pair or not. If you have a trigonal planar molecule, that means all 3 electron groups have their atoms meeting at the end. That is very important. The difference between bonding pair and lone pair is the bonding pair has the atom at the end of this pair of electrons. Lone pair, no. So we can have a certain group of molecules that has the same spatial arrangement as electron group arrangement or electron group geometry. We call it trigonal planar. And of course, there will be no lone pair. The bonding angle is 120 degrees. So that's why when we say molecular shape will be the same as electron group arrangement if there's no lone pair, because every electron group will have the atom at the other end. What happens if we do have a lone pair? That means there will be no atom on the other end. I'd like to remind you here, lone pair cannot be seen or cannot be detected. So that is why we take away the lone pair. This is what we have left as a shape of the molecule. Better way for us to describe it, bent or V-shape. Why the V-shape? Because we understand there's going to be an electron group on top of it in order to make it isosymmetric. And it has to be lone pair. Why? Because there's no atom on the other end. So that's a pair of electrons that cannot be detected. For bent, the bond angle here is somewhere close to 120 degrees. Less than, about 2 degrees less, right? But it's still in the neighborhood of 120 degrees. I'd like to call your attention for this value in the next few minutes. So this band actually can be derived from this trigonal planar arrangement from electron group because one of them cannot be seen, as we call them as lone pairs. For 4 electron groups, that definitely is going to be 3-dimensional. And for 3-dimensional, so we use different way to describe the spatial orientation of the bond. So say if you use dashed for the bond that's in the same plane as the screen, and the solid dash, that means the bond's coming out of the screen. The dash wedge indicates the bond going into the screen. In this way, 4-electron group has the arrangement of tetrahedral. It cannot be changed. And this is the bond that are coming out. This bond is going into the screen. And this is how we describe it. This is 3-dimensional geometry in 2 dimensions. All right. Remember, as we said, as long as I find out the number of electron groups, the geometry is pretty much set. But the shape is different because shape depends on just how many bonding atoms we have for these electron groups. If every single electron group has a terminal atom, then the arrangement is the shape of the molecule, which is tetrahedral. Again, I like to point out there's no lone pair in order to reach the same geometry. And here I lay out some of the examples that have this geometry. And if we have one lone pair, so say if you have one lone pair on the top, remember that one lone pair cannot be seen, right? So after we removed it, this is the molecular shape. We call it trigonal pyramidal. And we have a triangle at the bottom from these 3 atoms, and the central atom is going upward a little bit. So we call it trigonal pyramidal. That is because we see the one lone pair, and the bond angle must be less than 109.5 degrees. From 2 degrees, about 2 degrees less from its typical bond angle. And molecules like ammonia, ions like hydronium, H3O+, or chlorate will have this geometry. You know what happened if I got 2 lone pair of electrons? If I got a 2 lone pair of electrons, that means I have a 2 lone pair of electrons that cannot be 2 electron groups that cannot be seen. So this is what we have left. Again, that is going to be a V shape. Only this time, this V shape will have the bond angle that's around 110 degrees. So the bond angle here is about 110 degrees. Remember, we have a band with 3 electron groups as its molecular shape. The bond angle there is 120. That makes the difference. If we find out the V-shaped structure or band structure with the angle 120 degrees, we know there will be 3 electron groups on the central atom. If we have the bond angle that's around 110 degrees, we will know that's going to be 4 electron groups. Bond angle is critical in order for us to determine the number of electron groups on the central atom, particularly when the species has the same molecular shape. Bond angle is the key for us to recognize just how many number of atoms of the electron groups on the central atom. 5 electron groups is what we call trigonal bipyramidal, because we got one trigonal pyramidal from the top, second from the bottom, so that is why we have it. That is for 5 electron groups. When we look at this particular geometry for 5 electron groups, we find out that those electron groups are not entirely equivalent to themselves or among themselves, because we got a 2 that's pointing north or south, and we got a 3 perpendicular like equator on our Earth. So that is the reason why we call the 2 north and south as axial and 3 as equatorial. So we have 5 atoms with 2 very different spatial orientation. And that will make difference once we determine where we're going to put the lone pair of electrons in this particular arrangement. All right, start with 5 terminal atoms. The molecular shape is going to be trigonal bipyramidal, just like this one. So if I got 5 terminal atoms, and this is a trigonal bipyramidal, same as this. Again, in order to have molecular shape same as the electron group arrangement, there must be no lone pair. And you see bond angle is equal to those typical angles, 180. So that is 180 here. And we see 120 between or among those electron groups in the equatorial, and 90 between the axial and the equatorial. If we do have one lone pair will occupy the equatorial position. How do we know that? That is because we find out if we have a lone pair of electrons occupied on the equatorial position, that will introduce fewer 90 degrees angles. Remember, 90 degrees, the closer the angle, the smaller the angles between the electron groups, the greater the repulsion. Okay. Let's see. If we have a lone pair on equatorial position, let's see just how many 90-degree angle that we have. This is the one, right? Just like the one between the axial and equatorial, so that's 90 degree, and that is another 90 degree. So we have a total 2 90 degrees if we have the lone pair on equatorial position. Say if we have this as a lone pair, then if we have this lone pair occupying the axial position, how many 90 degrees that we see? And I'm going to use the green one. And we have 190 degrees here. That's going to be 190 degrees between this electron group and that one. And of course, that's going to be the third 90 degrees from this axial to that end. So if we put a lone pair group, lone pair of electrons on the axial position, we have a total 3 90-degree angles. 3 90-degree angles meaning more repulsion. So it's become more stable if we put the lone pair of electrons on the equatorial position. And that is what we call seesaw as its molecular shape. Why we call it seesaw? Because if you rotate it 90 degrees, this is what we see. It's a seesaw, right? So we got 2 kids sitting on the end, going upside down. So that's what we call a seesaw. For seesaw, the bond angle is going to be less than 180 degrees, less than 190 degrees, and then less than 120 degrees. Basically, as long as we have lone pair of electrons, it's most likely going to have the less angle than the typical ones. Okay, the less the value from their typical bond angles. All right, let's see what happens if we have a two lone pair of electrons, because for one lone pair of electrons, we understand that's going to be a seesaw. So what happens if we have a two lone pair of electrons? Again, the second lone pair of electrons still occupying the equatorial position. Same argument, because this way only two 90 degrees are introduced. And the rest, as we can see, remember, those two cannot be seen. So what we do see here is T-shape. So the molecular shape for two lone pair in this 5 electron group arrangement, T-shape. The third one, third lone pair is still going to the equatorial position, so that makes the entire molecule linear. And of course, the bond angle is going to be back as 180 degrees because these 3 lone pair electrons become symmetric. So just how many molecular shapes we can derive from these 5 electron groups? I think there are 4 of them, right? So we got trigonal bipyramidal with a 0 lone pair, seesaw with 1, T-shape with 2, linear with a 3. As a matter of fact, are all derived from electron group arrangement because of lone pair electrons. For 6 electron groups, as we understand, that's going to be octahedral. And I do not know whether there's going to be a good enough picture for us to realize that there are 8 faces for this particular geometry. So we call it octahedral as the electron group arrangement. So it's not EP, that's EG. If each electron group is a bond, we got the same arrangement as molecular shape, so we call it octahedral. And here are some examples, as you can see here. And all of because there's no lone pair. With the 1 lone pair, all right, so that's on the bottom. It's on the top too. It can be on the top, but if you rotate it, so we can put this at the bottom. So it doesn't matter. So with the 5 electron, so with the 5 bonding pair, 1 electron, 1 lone pair. So the shape here is what we call the square pyramidal. Bond angle less than 90. And for octahedral, that's equal to 90 because that is the perfect symmetric shape. With a 0 lone pair, octahedral. With the 1 lone pair, we got the molecular shape square pyramidal. And if you got the 2 lone pairs, as you can see, we got square planar. Square planar, this is very symmetric. The bond angle goes back at 90 degrees. And of course, here are some examples that have the molecular shape as we discussed. All right, so just what is the general procedure for us to practice the VSEPR theory or VSEPR model? Remember, first step is to draw a valid Lewis dot structure. Here I just lay out some typical steps for us to write the Lewis structure. First, we need to determine the total valence electrons, and we're going to set atoms, especially central atoms. Remember, central atom must be the one with the least electron activity, with the exception of hydrogen, of course. Then we give electrons back, and we're going to take care of octet for the central atom, but we need to be aware these 3 atoms and a little bit more. This is something that we're going to discuss in the second half of the lecture. Once we have a valid Lewis structure, we're going to focus on the central atom. Okay, for the VSEPR, we're going to count electron groups. We're going to count number of bonds, number of lone pairs. For the regular exam or homework assignment, we do not see the radical, so we can pretty much take that out. So we just count number of bonds, number of lone pairs. Remember, number of bonds, it doesn't matter whether there's going to be double bond or triple bond or even single bond. It doesn't matter. We count them as a 1 electron group. Then, based on the sum of these bond and pairs, we determine electron group arrangement. So that comes to first, before we start thinking about the molecular shape. With this particular electron group arrangement that we determined, then we derive or determine the molecular shape depending on just how many lone pair electrons that we have on the central atom. Now, let's summarize the various electron group arrangement as well as molecular shape. Remember, it is electron group arrangement that has the higher priority, which means we have to determine electron group arrangement first. With a 2, there's only 1 molecular shape, linear, same as the arrangement. With the 3 electron groups, we can have 2 different molecular shapes, depending upon whether we have a lone pair. If we have a trigonoplanar, the bond angle is 120 degrees, and with a lone pair, I want you guys to realize it is less than the typical bond angle. Speaking of bonds, these are the ones that we can actually detect. The thing that we cannot detect is the lone pair. So that is the reason why shapes vary with the number of lone pairs. But the lone pair or not, lone pair itself should be counted as an electron group. That is the reason why, don't forget, we determine electron group arrangement first. With the 4 electron groups, we can have 3 different molecular shapes: tetrahedral, trigonal, pyramidal, and V shape. And for this V shape, I want you guys to realize it is around 110 degrees. All of this come from 1 particular electron group arrangement. Again, determine electron group arrangement first. We do not go that other way around, right? We just find out just how many electron groups we have on the central atom before we determine the shape or the geometry. 5 electron group arrangement gives us the most number of different molecular shapes. As we see, TBP, trigonal bipyramidal. That is a short for trigonal bipyramidal TPP, or seesaw, or T-shape, or linear. And for 6 electron groups, we can have 3 different molecular shapes. So before we put an end of this lecture, I just want you guys to know, when we deal with a VSEPR, we determine electron group arrangement first. How do we know the electron group arrangement? Central atom. We do not have to worry about whether there's going to be terminal atoms or not. All we have to do is to count just how many electron groups that we have on the central atom. We determine the arrangement. Then we go to the shape from top down. That is the priority. We have to determine this thing first. That is the end for this lecture. And we'll start the second half of the lecture of chapter 8 by practicing the loose dot structure and the VSEPR using 2 questions in our homework 18. So I just want you guys to have homework 18 ready when you go over the second half of chapter 8. Thank you.